Hey students, I thought I'd go ahead and make you a little video solution for two reasons. The first one being, I know you're really curious on how you did, and this is a chance to kind of answer those curiosities and to self-correct. That is, take a look, see how you did, get a rough idea of what your score is, and like I said, kind of self-grade. I like to do that because it's difficult for me to, give you direct feedback written on a PDF form. And so this is the best way I find online to give you the feedback, and you can look at as much detail as you want on this, what will probably be a long video of the solutions to the exam. And so that's kind of the main reason. And the second reason also is, not only is this hard material, so I'm sure you realized it took you a long time to do the homework as well as the test. I think this is probably the hardest of the whole 3-semester sequence, but it also takes me a while to get all these graded. And so you guys have done a lot of work, and it's a long test, and it takes a long time to grade it also. And so I thought this is the best way to give you feedback in a short amount of time, but I'll really need the whole weekend to get everything graded. All right, well, let's dive in here. Here's question number one. And I hope you kind of see the structure here, that we start with kind of an easier part that leads into an extension into a more advanced part. And that's true in question 2 and question 3 also, where there's a part A and a part B. And so the simple stuff is, what if you just have point charges? And that's what we have in A here. And so it talks about this 3 microcoulombs that is 10 centimeters above point P, and a second one that is 5 microcoulombs, 8 centimeters to the left of P. Then we place a 2 microcoulomb charge at point P. What is the magnitude and the direction of the force on this 2, and it's not listed in the chart here, so I'll add it, this 2 microcoulomb charge at point P. So there's a lot of work on this problem, so maybe I'll try to get it all on this front page. That may or may not work. In fact, maybe I'll just even pause from doing this question explicitly and kind of remind you of the video lecture. You might know that we talked about this pattern, that there is a connection between the position of an object, the velocity of an object, and the acceleration of an object. And for that matter, the force of an object. And all of this was done in mechanics, Physics 121 in this case. And so we came in this semester saying, okay, if you get the net field, which you can get by summation of all the individual fields from a bunch of points, then that'll give you the net field, which then gives you the force and the acceleration, blah, blah, blah. But I think you're seeing then this problem, number one, is straight from this first step in chapter 23, Coulomb's law, because we know how to get the electric field from a single point. It follows this equation: Coulomb's constant times that charge times that distance away. So if we do that and say, okay, how much electric field from the 3 microcoulombs is at point P, and how much of a field do we get from the 5 microcoulombs at point P, we would have the 2 fields. And that's this part of our little diagram. We got the 2 fields, we combine them together, we get the net field from there we get the force, and then with this problem we can stop there, but in a more advanced problem, if you will, we would then divide by mass to get acceleration, integrate that to get velocity, and integrate that to get the position of the particle. And so we're looking kind of at, this part of the sequence. Maybe I'll circle it in blue. And so let's do these 2 points here. And so using this equation, and I'll call it field number 1, we can apply this equation to this charge right here. And so grabbing my calculator, I'll go 9 times 10 to the 9th times the charge of the 3 microcoulombs divided by the distance away, and I better convert it into meters. It says 10 centimeters, but 0.1 squared. And I get a field value of my first field, which again I'm calling number 1, of 2.70 times 10 to the 1, 2, 3, 4, 5, 6 in newtons per coulomb. And if I do the magnitude of field number 2, which would be coming from this one here, I'll do 9 times 10 to the 9th times 5 times 10 to the negative 6. The distance is 0.08 in meters squared. It says 8 centimeters, but little unit conversion there. But it looks like, let's see, 1, 2, 3, 4, 5, 6 times 10 to the 6. So this would be 7.03 times 10 to the 6 newtons per coulomb. So that's our 2 fields, and that's just part of the diagram right here. You know, what is the field? Okay, so then I'm going to combine these 2 fields, although I guess you could also do the forces separately and combine the forces. I'm not sure which is better. Either way works. But why don't, so I just kind of follow along in this diagram. I'll do it in this diagram sense. And say, all right, field number 1, since this is a positive charge, would look something like this. It would point down. And field number 2 would point away from its positive charge, and it would look like this. So ultimately, I would have a field where I combine the 2 together. And so let's call this the net field. But I have to do Pythagorean's theorem here. They're at right angles to each other. And so this would be the total net field here. And so let me come up and grab that first field and square it, and add to it the second field and square it, hit enter and do a square root. And so we're looking at about a 7.53, and this must be 10 to the 6th. 1, 2, 3, 4, 5, 6, yeah, newtons per coulomb. All right, so again, back to this diagram here. Here's what we've done. We've taken the 2 points. We've got the field separately. Now we've put them together, and we got the net field. So now to get the net force, it's kind of an easy step. Net force is just whatever charge you put there times that net field. So I've got the field, and I'll just multiply it by the charge we're going to put there, which is the 2 micro. And so we get a total force magnitude of 15.1 newtons. And so there's the first part of the question. What is the magnitude? And the direction would be, you know, down at some angle here. I'll call this theta. And I suppose we could do that by the components of the field. And since we have the y component and the x component and also the magnitude, we can use any of the trig functions. Maybe I'll do the tangent function. And so the tangent would be opposite of this angle, which is the y component. So that's number 1, 2.7 times 10 to the 6th over the 7.03 times 10 to the 6th. In fact, the 10 to the 6th will cancel off. And so I won't even mess with those. And I will then just have, let me check, am I in degrees? I am, okay. And so let me go inverse tangent of 2.7 over 7.03, and I get about a 21 degree angle down, 21.0 down, or you can put a negative or whatever, but there is the answer to A. What is the magnitude and the direction? Now, probably didn't leave enough room on my paper here for B, but that's okay. I'll get another sheet, or maybe I'll do it on the, continue on the back side. But reading the problem, hopefully you see kind of the same logic. A little more advanced, though, because we don't have individual charges. And so we don't get the field by this simple equation. We still are going to then find the field from one rod and another. And so let's start there. Why don't we do something to this effect? Why don't we just say that we have a rod, and maybe you remember doing this in class. I know it's also one of the examples done in the book. In fact, some of you, I noticed flipping through, and this is fine, just looked up the equation for a rod, and that's fine. You got it straight from example, I can't remember what example it was or is. Let's see, I have the book close at hand. So somewhere in here, I do a bunch of points first, and so this is kind of what we've done. Like right here, we've added up the field from 2 points. So what we just did is a good example of 5. Then it's right here in section 5, they get into continuous charge distributions. And it looks like number 6, and they just do a rod right there. And so part of me is tempted just to grab the end results here of example number 5. But that wasn't my intent. My intent is not to have you memorize a bunch of stuff and just kind of regurgitate it, although it is open book and open notes, so I guess you're not really memorizing it. But it would be worth taking a moment to go through this, because here's the logic, if you didn't catch it before the exam, is that if you know how to get the field from a single point, then you can get it for any shape, including a rod, by just thinking of this rod as being chopped into little tiny pieces, little points, and adding up all these little chunks. And so why don't I just kind of start with maybe, some little chunk right in the middle. I'll call that DQ, and say, okay, now that DQ is going to make a little field right here. Call it DE. And the logic being that if we take this idea of a point charge, we could say that Coulomb's constant times that little chunk of charge divided by the distance away would be the field from that little chunk of charge. And so, therefore, by an extension of that, to get the total electric field, we would have to add up. That's what an integral is, right? That's the whole idea, that the definition of an integral, the integral of f of x dx, is the limit as delta x goes to 0 of an infinite summation of f of x delta x. And so anytime you find yourself needing to add up an infinite number of tiny, tiny pieces, in fact, it would be an infinite number of infinitely small pieces, you do an integration. That's why we use this little squiggle here, which is kind of an elongated S for summation. All right, so that's what I'm going to do here. I'm going to do a summation, and I'm going to do a summation on these individual chunks of charges. And so here's my integral K T R squared. And I need to apply each of these appropriate for this particular rod. And up here, the rods, length that's a charge, are rods instead of length, each with closed points respectively. What is the magnitude and direction? So really they haven't changed anything other than to spread out the charge. And so this becomes then, and maybe I should put here, I'll put it up here. Lambda would be a little bit of charge spread out over a little bit of length. That's kind of our traditional symbol of what we mean by a linear charge density. But you can see in this equation, moving the dx to the other side, that dq is lambda dx. And so now I'm going to be adding up along this rod. And maybe what I'll do is I'll call this my origin, and I'll have x getting bigger to the left. That's kind of opposite of tradition, but it's just kind of the way I drew it. I probably should have drawn it on this side like the book had it as an example 6. But we would then be adding up from however far away this is, which you're in your book example, they called that an A, and they called this then L, the length of the rod. And so the first chunk of charge would be at a distance of A, and the last one would be at an A plus L. And then the distance away is the x-axis. And so the total electric field from a rod, then, we can pull out constants, and then we have just an integral of dx over x squared, which is 1 over x. And we're going to evaluate it from A to A plus L. And so we get this k lambda. And then, of course, we've got our negative 1 over x plus L minus a negative 1 over A. And we could even simplify this, although that's probably good enough for, well, maybe I'll put a plus here. But that's good enough probably for the exam. But in the example I was referring to in the textbook, they went ahead and they did this. They said, well, the lambda is the charge on the rod, so let's call that Q divided by its length. Okay. And that this then would have a common denominator of A times A plus L. And to get that common denominator, you would have to multiply this top one by an A, and this one here by an A plus an L. And so the two A's cancel off, and then you're left with an L, which actually cancels with that one. And so you end up with Coulomb's constant times the charge on the rod divided by A, the distance to the nearest part of the rod, and then this is the distance to the furthest part of the rod. And I think that's what they have. Let me grab the textbook here. Yeah, so there it is. And so that's what they ended up getting in this example number 6. Okay. Now, like I said, didn't expect you to necessarily pull that out of the equation of the book. Otherwise, you're spending too much time memorizing the book and the formulas in the book. The idea is just memorize a point, because the theory is if you know a point, you can get any shape because it's just a bunch of summations. And the rod's probably the easiest one. And I know that, on the homework, some of these shapes can take you a long time, like the cylinders we did. And that's just a little too long for an exam. But a rod's very reasonable. All right. So, like I said, you could have started right here, or you can kind of work it out. All right. So, knowing that this is it, why don't I then, actually, I'll just use my yellow pad here. Continue on with this number 1b and say, okay, so what is the strength of the electric field from number 1, and what is the strength from electric field number 2, where, again, number 1 is coming from this rod. Now, just out of curiosity, when it was all concentrated as a point, I got 2.7 times 10 to the 6th. And so stretching it out, that means some of this charge is further away. And so I expect to get a number less than that. So let's see. So grabbing my calculator and then using this formula here, I would go Coulomb's constant times that charge, 3 microcoulombs, divided by the distance away, that's 0.1. And then we get to the picture, that's that 0.1. And they said the length of the rod is 20 centimeters. So that means this furthest point is 0.3. Let me write that down. 0.3 away. And so that would be the A plus L, 0.3. So I'm going to put a 0.3 there. And I get, looks like 9 times 10 to the 9th here. So 9 times 10 to the 9th for this electric field. And I guess I should put the units. And so, like I said, it should be quite a bit less than this one. Good. And let's do the same logic for number 2. 9 times 10 to the 9th times its charge, which is 5, right, microcoulombs. Then divide by the A, the distance away, 0.08, and divide by 0.28. That's the distance of the end of the rod. That's the A plus the L. When you read the math, what does that mean? It means the, So by the way, this would be the geometric average is what we're really talking about here. And so we've got, looks like 2, 1, 2, 3, 4, 5, 6, 2, and it would round to 2.01 times 10 to the 6 newtons per coulomb. So again, smaller than what we got in part A, because we've taken this 5 microcoulombs and we kind of stretched it out. And so a lot, this charge is spread out. A lot of the pieces, if you will, of this charge are further away, making the field weaker at this point. And so that's what we would expect, a weaker field. By the way, we wouldn't expect them to go down the same amount because as you can see, the difference between the what I'll call the front and the back of the charge distribution is more significant for something that's close than something that's far away. In fact, something that's really far away, if you stretch it out, it's pretty much like it's still a point. You haven't really stretched it. This number is so much bigger than the length of the rod. But in our case, we're going to expect this to drop significantly or more so than this one. And so that's another way of saying, I guess I would expect then that this horizontal piece gets reduced by a bigger fraction than this one gets reduced. And so I'm expecting it to kind of angle down a little bit more than what we got before, which was 21 degrees. I'm going to expect this angle now to be greater than 21 degrees, if all that makes sense. But like before then, let's just get the net field. Okay, so the net field is what you get when you take field number 1, which is the vertical component, and field number 2, which is the horizontal component, and then you square them. So in my case, here's the horizontal, and I will square it, and here is that's the vertical one, that's the first one. And here's the second one, which is the horizontal one, and I'll square it. And then I will take the square root of all this good stuff, and I'm looking at 2.20 times 10 to the, this must be a 6, 6 newtons per coulomb, so that I can actually answer this question. And going back to our page 1 here in our diagram, this is really what I've done now. I got net force, and now I just multiply by Q to get the force. And so times that 2 microcoulomb. And so we're looking at about 4.40 newtons then. And the angle, again, like we did in part A, this would just be the inverse tangent. And the vertical piece is number 2.0 times 10 to the 6th. And then this is, can I just write this as 0.9 times 10 to the 6th? So I'll make that one smaller while I make that one bigger, so I can just cancel off the 10 to the 6th, so that I can go inverse tangent of 2.01 and divide it by 0.9. And, oh, did I... get those backwards? I did. I didn't like that answer. Let me try that again. Okay, so the vertical component would be from number 1 going down. So there's the 0.9. And then the 2.01 for the horizontal, which is our number 2. All right. So wouldn't that just be the complement there? Yeah, it must be in 24. But why don't I just be careful and make sure. Inverse tangent of 0.9 divided by 2.01, 24.1. Yeah, and so a little bit more than the 21 that I got in part A. Yay! And then you can put down, or you can put it as a negative, whatever you want here in terms of the mathematics. All right, well, I hope you did well on that one. Again, my grading is based upon logic, so I have a strong feeling that since there's a lot of details in here, you may have not gotten the first problem completely right, all 4 answers, but I have a strong feeling that you guys got the gist of it, and you found the individual fields, and you put them together, and you did your Pythagorean theorem. And so I suspect that there's going to be, things like 17 out of 20, or 18 out of 20, or maybe even as 15 out of 20. But most of it would probably be a pretty high score in terms of doing this. I hope, anyways, especially with number 1, because number 1's a straightforward one, the kind of a I'll call it a high school level problem where you have just individual point charges without any calculus. And then number 2 is some calculus. But even if you kind of got this equation wrong, still a significant amount of partial credit here. At least I hope so here. All right, well, let's move on then to question number 2, and I'll kind of explain it in terms of this diagram again, because if you also remember, this was chapter 23 we just did, and chapter 24 said, hey, there is another nice way of finding electric fields called Gauss's law. And it is kind of a clever way of using the idea of flux and our integrals. And it looks kind of scary at first, but when we do a lot of symmetry, it makes things work out real nice. And that's what this problem is all about. And sadly, the copy didn't come out real clean here. This is... looks much better online, and there should be kind of a slab in here for B, and I'll point out when we get to B, it's kind of important to realize to get the symmetry. Now, it was kind of our argument here that this was only valid with a lot of or useful, I should say. It's always valid, but only useful with a lot of symmetry. And we put the origin in right in the middle of this slab. However, well, let's do the easy one first. So this is Gauss's law from a plane. I don't know if it's worth showing you the textbook here. But when we get into chapter 24, here we go, and the author starts introducing you to flux, and then, okay, so here's Gauss's law. The author says one of the nice ones to do is inside a charged sphere, because that would have been really hard to do by Coulomb's law. But here's the one we're looking at here. And so this is really what it's asking you to repeat. And so there's not a whole lot of complicated steps. In fact, your author probably doesn't go into enough detail, so I think I will if you're following along here. But we really need to understand this one to do part B. So I'm hoping, again, with partial credit, you'll be able to, okay, look at this one. Hopefully you already know it from the lecture, but also hopefully you're able to just say, okay, I can do this one. And you kind of get you started for something that's a little bit more advanced here. Now, my diagram is twisted compared to that one. That one had it horizontally. Maybe I like it because it kind of fits with the video camera a little bit better here. But I kind of like to do this. This is going to be my Gaussian surface. I'm going to take a little sticky here and say that the charged surface is this piece of paper. And this will be my Gaussian surface. Although I'm going to imagine it punching through something like this. And what's nice is we have to have a closed surface. And if I can get this a little better roll. Maybe not. But when you do a closed surface, we would have to include this top part, what I'll call the top cap, and the bottom cap. And so if we start by saying an integral over a closed surface, we would have to replace it with, 3 integrals by saying I'm doing the top cap, and I'm over here, the bottom cap, and then the part that wraps around the face. Now, this dot product is going to have an EDA cosine of theta in each term. And so let me extend this down to here, A. On the top cap, we're going to argue that the electric field is the same everywhere on the surface of this top cap. And the argument goes something like this, that imagine yourself standing up here. If you were to walk a little bit anywhere along here, you would, of course, see the same charge distribution if this is truly a big or infinite sheet, because even though you moved a little bit over here to the left, you're still way far from the edge. And so whatever electric field it produced when you were standing in the middle of this top cap, you would get the same when you went to your left or you went to your right. And so we're going to say the electric field is a constant over this top cap and pull it out in front. We're also going to argue that same symmetry here, that because that charge is the same, it must be pointing straight upward. Now, that is, the electric field must be pointing straight upward, which is actually the same as the normal component, and so this angle is 0 degrees. Both the dA and the electric field are straight up. But of course, the argument on that is what we call, a symmetry argument here, that if you took this point here and you kind of, rotated it, if, you did this, because this sheet is so big, the charge distribution that would still be underneath you would be exactly the same. But if your electric field was not pointing straight up, your electric field was kind of angled a little bit and you rotated it, well, then it, all of a sudden you would have an electric field in a different direction, yet the charge underneath you, which created the field, is still kind of exactly in the same position. And so you have to get the same direction to the field. And so that's why we can rule out the electric field being angled at all. And I'll say it again, because if it's what we call an indirect argument. If it was angled and you rotated it, now you get a new direction, yet the charge underneath it still looks the same. That's not possible. And so that means the only place the field can be is in such a way that when you rotate it, it doesn't change its direction. So that means it's along that axis of symmetry, which is pointing straight up. And so that's the argument about the top cap. And it's the same argument for the bottom cap. This is cosine of 0 degrees. And it's also why we have the argument of cosine of 90 degrees for along the face, because the normal would be perpendicular to this surface. And so if I get kind of something to point a vector, what do I have? Maybe I'll use this top of a pen, but you know, the normal vector would be pointing to the left here, or down on the screen here, or to the right here, or to the top of the screen when I put it over here. But the point is, the direction of the normal vector is going to be 90 degrees, no matter where it is along this face, because the electric field, we just argue, has to be pointing, you know, straight up. And so that one is 0. And so you can kind of see why these have to be the same. So this comes out to be 2EA for one side of Gauss's law. Now, I guess I didn't write it out in its fullness. I think I did over here. Yeah, so that's the left-hand side of the integral. The other side is the charge enclosed divided by epsilon naught. And if we just have this sheet, then, when we put this Gaussian surface right in the center, by the way, notice it had to be centered. The Gaussian sheet that I'm creating needs to be right in the center here so that I can make the argument that the two electric fields on the top cap and the bottom cap are the same, because they're equal distance away. Okay, that was important. It's also why, you know, the bottom cap and the top cap look the same, and no doubt then they came out to be the same integrals. Now, the reason I say all that is because if you put this surface right through the middle, then this surface does enclose some charge. If you could look down inside of the Gaussian surface, you know, this would be like punching a little circular hole right there. And so that charge right there would be inside of this Gaussian surface. And of course, then if we use the traditional sigma for the charge per area, then we just have to say that the charge inside there would be whatever this charge density is times the area of that little circle. We don't even need to say that the area of a circle is pi r squared, because at this point the two a's cancel off, and we can then get what we're asked to show, which is that the electric field is the surface charge density times 2 sigma. And that's, like I said, was done directly in the book. We did it in class. We did it in a video lecture. You did it on the homework. Hopefully that one went really well for you. B then is just an extension of that, but not too much different. And so let's do this same logic. The only difference in B is instead of having a sheet, we have a slab. And the slab just means we have some thickness to it. And that's why I drew it earlier and said, okay, we have a size of A. Oh, that looks like part A. We have a thickness of A here. And so it goes up to Z equals to A over 2 and Z equals to minus A over 2. And so if I give it a little thickness, so maybe now, instead of using my piece of paper as the sheet, I'll use this full sticky pad as the slab, because I'm going to put another Gaussian surface. And here I need to apologize for a little typo I had. So I graded it either way because the dimensions I gave you, which is 3 centimeters up, is what I intended to give you, in the sense that this would go, this Gaussian surface I'm going to draw, which is, 3 centimeters up. So from the center, and again, that's symmetry, so I'll put the center of the Gaussian surface right in the center of the slab. So if this is the center of the slab, I will line it up with the center of the Gaussian surface, something like this, okay? And our Gaussian surface would extend above the slab, and for that matter, also below the slab. Because if the slab is only 5 centimeters thick, the slab only extends upward for 2.5 centimeters. But yet I put in these words here inside the slab, and that's where I'm really bumming. And so I will grade it either way, that you have a Gaussian surface that is still inside the slab, or you have a Gaussian surface that extends above the slab. So let's do both, because I confused it with and giving it both. Hopefully you saw this crossed out. I noticed it right as the test started, and so I quickly went on Canvas and covered this up. And so depending when you started the exam, I'm hoping most of you didn't even see this. But some of you probably started and loaded it directly at 8 o'clock, and you saw that. And I don't think it goes away unless you refresh your page. But any other case, like I said, I owe it to you guys to grade both options. And so let's just talk about it. But I'm hoping the first part you see, where I do an integration on the closed surface, I'm going to get the same thing. I'm going to get the top cap. I'm going to get the bottom cap. And I'm going to get the face. And all the logic is still the same. And so we're going to get 2 times electric field times the area of the cap right here. Just like, and I didn't put area of cap, but that's what was meant there. And the area of the cap and the area that punched through were the same. That's why they canceled off. Okay, so this is still the same in terms of our argument about symmetry and how the electric field, we have to know how 0 degrees on each of the cap and 90 degrees on the face, and that the electric field would be a constant over the cap, and you can pull it out. And so that hasn't changed. What has changed, though, a little bit for B is what's inside. We really can't talk about a surface charge density anymore, because we don't have a surface charge density. Now we have a volume, so there should be this rho. And so rho is the charge per volume. And the volume of this, and again, if you put this right in the center, would be the cross-sectional area A times this length here. And if we call up from the center Z, then it would be A times 2Z. See, because if you go from here to here, that Z, the whole length of this is 2Z. And again, then the A's cancel off, even the 2's cancel off, and you get the electric field equals the charge density times Z over epsilon naught. And then this is where I would say you're fine with 2 answers. The first answer is, if we're talking about the charge inside, then our distance up would really only be 2.5 centimeters, because then we run out of charge. And even though our Gaussian sheet goes up to 3, we don't want to put that into our equation of 3, because that's not where there's any charge. On the other hand, if you didn't notice my mistake here and said, and go, oh, it's inside, then you would use 3 centimeters. So those are our 2 options. So to finish this problem, let's do a calculation here for both cases. Let's see, the charge density is given as, just readjust this, 2 net 2, oh, there's what I'm missing, times 10 to the negative 9, 2 nanocoulombs. And if I divide that by 8.85 times 10 to the negative 12, I'll just put those 2 together. These 2 together is about 226. So if I take as the problem was intended by me as 0.025, I get a 5.65 newtons per coulomb, because again, the last part of the Z does not include any more charge. But if the surface is actually still inside, as my mistake has it here, let me take that original number, instead of multiply it by the 2.5 centimeters, I'll multiply it by the 3 centimeters, converting the units. So this should be 6.78 newtons per coulomb. So either one of those answers is very acceptable. Again, my apologies for putting that word inside, and I hope you're one of, hopefully, majority that never saw that word. And so there was no confusion. You just went right to the 2.5 centimeters. Okay, so with that in mind, let's move on to number 3. And again, you'll kind of see that same setup that you saw with the other ones, that, hey, here's an easy one, 2-point charges, kind of a high school level type of problem. And then now let's throw some calculus into the mix. And then this one, hopefully you can see the energy, and that is this exactly out of chapter 25. If I come back to this picture, this was our argument here, that there is this thing called electric potential. And what we like about electric potential is it gives us a way to get velocity using conservation of energy. Okay. Now, we also like it because taking its derivatives can get us electric field. And so we said that there's 2 reasons we care about electric potential. One of them is to get us the field, which we're not interested in this case. We're interested in velocity. So we're going to go this route. And we also said, kind of like this logic, that if you know the potential from some individual points, you can add all those points together to get the total potential. And from that, you can use conservation of energy. And this is the logic I'm going to do. So let's start here for A. We have the potential created. In this case, it's fairly simple. We have just one other charge. And so how much potential do we get from this fixed charge at this location? And so I'll just put here that the potential we learned for a point charge is Coulomb's constant times charge divided by that distance away. So for part A, when I say let's look at the change in potential, which is final minus initial, I'll go ahead and put, okay, what is the final potential? Now this diagram, hopefully you caught in the reading here. Let's see, the fixed charge is negative 7.5 microcoulombs. and it is placed 1.25 millimeters from a movable one that has a negative 5.50 microcoulomb. So two negatives repel. And I guess it doesn't matter which one you call fixed or which one you call movable. What is the speed of the movable one when it's 1 meter away? So this diagram shows where it starts and then it gets pushed away. So this would be over here, Coulomb's constant times this negative 7.5 microcoulombs divided by its distance away, which is 1 meter. And so that's what the potential from this one when this one's way over here somewhere. And then we have Coulomb's constant times that same fixed charge that's creating the potential. When it is only a little over 1 millimeter away. We hopefully also are a little careful with our units here. Coulomb's constant we're going to be doing in the units of meters and newtons. And so we need to put those distances involved here. But now we can do our calculation. And as far as, calculating this number, perhaps I'll just go ahead and do the Coulomb's constant and multiply it by the charge and just kind of factor those out, because then this, once I factor it out, would be 1 over 1, so that's 1 minus, if I factor that out, it's 1 divided by 0.00125. And so this would be 5.39 times 10 to the 4, 5, 6, 7 volts. And so there's the change in the potential. Now, that is supposed to be the hard or new stuff for this problem. Although maybe I should put in my diagram like I did energy. Because once you get the change in potential, the change in potential energy is pretty easy. It's just, okay, how much charge do you place in that change in potential? So the change in potential is created by this fixed one. And the charge that I'm going to put in that presence of the fixed one is this movable one, which is negative 0.515. So if I just take that and multiply it by the negative 0.515 times 10 to the minus 6, I'm going to get a change in potential of negative 2.969 joules. And the negative is good because we know that the change in kinetic is the opposite of the change in the potential. So when we decrease in potential, that means we gain kinetic, and that's why this is going faster and faster and being pushed away. So this is a positive 296.6. And the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And then this one we can ignore because they say they put it here in rest. Is released from rest. So the initial speed is 0. And so that means if I put in my mass, and want to be a little careful, this needs to be mass in kilograms. They gave it to me in grams. But now I can solve for final speed. So I'll take this number, maybe first of all I'll get rid of the negative, and then multiply it by a 2, then divide it by the mass, and then finally take the square root of all of that. And we're looking about 230 meters per second. Yay! It's all pretty fast, and rightfully so. In fact, by the time we kind of finish this exam and start working towards what I'll call practical problems, application problems, we'll see that this is why we like these electrical forces. They can make little tiny things go really, really, really fast. And so all of our things transition in like nanoseconds of time. And so we build things like oscilloscope and all kinds of other devices that have response times in the billionths of a second. Now, B is kind of that same logic. But it is taking this fixed charge and extending it out. And so we need to know the potential from a rod now. And hopefully this looks a lot like our logic that we just did back here in 1B. That if we know it from a point, in this case it was an electric field, and we do know it from a point, we can just add up an infinite number of them. We can apply our calculus here and get in this case, we got the electric field from the whole rod. I'm going to do exactly that same logic and say, all right, let's apply it to that same logic, but this time, instead of adding up a bunch of electric fields, we're going to add up a bunch of potentials. So maybe I'll kind of do that same logic here. So here's my rod. Maybe I'll even use the same notation as before. Let's say we're a distance A away, and the rod has a length of L. And last time we divided it, if you remember, by a bunch of little chunks. I use the blue marker to kind of show it, and I'm going to do the same thing. Maybe I'll color one in and call that a little chunk of charge dq. And so the amount of potential dV at this point from that chunk of charge dq would be k dq over r. And so to get the total potential at this point right here from this rod, so maybe I'll say from the rod, is we've got an integral of dV. Okay, so I'll go integral of k dq, and I'll put this r here for a moment. But again, like we did back here, let's call lambda the charge per length. And so that means the dq is lambda dx. So I'm going to replace this with lambda dx. And also, again, like we did here in 1b, is then the distance away. If we call this kind of the x-axis here, we would be, starting with this first chunk of charge at a distance of a. So here's a. And we would add it up until we got to a distance of a plus L. And of course, that distance away is now x. So, I guess I switched the directions here so this one looked a little bit more like this picture. Oh, I guess that's why I did that one, so it looked like this picture, but the pictures are reversed. But the logic, hopefully, you see is the same. And so, again, we just have this integral to do, which is dx over x, which is a natural log. And we're going to evaluate it from a to a plus L. And so this would be k lambda natural log, and then we would have a plus L minus the natural log of a. But if you let me use the property of logarithms, if you subtract two logarithms, that's the same as a quotient of a single logarithm. And so I'll just have this one. And in fact, if you let me take one more step like we did in 1b, we could say this is the charge divided by the length, and then we have ln of a plus L. That's the end of the rod. And then this is the beginning of the rod. Okay? And so I'm going to take advantage of that equation. Makes me wonder if this one was done for us in chapter 25. I remember, showing you that the author added up a rod for the electric field. I don't recall him doing an electric potential from a rod, at least in the examples. I think there was a homework one he did. Oh yeah, so here it looks like here he does a ring, and then from a ring he does a disc. Oh, and he does a rod, but not quite the same angle. He does it perpendicular to the end. So, okay, so you can't directly maybe look this one up from the examples. Looking at the homework, here, I guess here it is though. Be number 35, length axis. Oh, this is a non-uniform one. This is actually harder. It could be in here. Here's another rod, but again, a harder one. It's perpendicular to the rod, and the rod's offset. So he's got some harder ones in here, but he doesn't have this one. This one's, like I said, hopefully pretty straightforward and kind of makes sense, I'm hoping here. But that would be the equation for the potential. Maybe I'll just circle it. I guess I'm kind of out of room on this page, so let me grab another page here and then call this, let's see, 3B. But I'm going to do, again, this logic. Let's find the equation for the potential of the rod by adding up a bunch of points. I got it. And so now let's do the change in the potential. It would be the final minus the initial. And so remember in 3A, we had the equation for the final potential when the particle was 1 meter away from the, and this time it's going to be 1 meter away from the closest edge. And then over here, it's going to be, starting at 1.25 millimeters from the closest edge. So maybe I'll put this equation into the screen here and say, all right, I need to apply this. So this would be Coulomb's constant, 9 times 10 to the 9th, times the charge of this rod. And so this rod is the negative 7.5 times 10 to the minus 6. It's, again, the rod that's making the potential, times the length of the rod. And so we stretch out the charge to 20 centimeters, so I'll go 0.2. Okay. Times ln of, and so remember, this is the distance away plus length of rod. And so in our case, this would be 1.2 meters. So this is the, when this has moved away, way over here, the final potential, we've got a 1 meter and then a 0.2. And then this is over 1. And so that's the equation for the final potential. So we have to subtract this same equation, but at its starting potential. All right. And so its starting potential would be, okay, how far is the end of the rod? And so I guess it's 20 centimeters plus a millimeter and a quarter. Maybe I better watch my units here. Is that right? Let's see. 20 centimeters. And then if I add the millimeters, yeah, I would get 20.125 centimeters. Move the decimal, so it's 20.125, yeah. So that's the distance away to the end of the rod. And then the far end of the rod, and then this is the beginning of the rod, just the A. So millimeter, yeah. All right, so then I can get what I'm looking for. And I guess I would do the same kind of thinking I did back on number 1, that this change in potential, I would think, should be a little bit less, maybe even quite a bit less. Yeah, quite a bit less, because I'm taking this charge and I'm now spreading it out. And so instead of having all this charge real close, a lot of the charge is spread out further away, giving it less potential for the spot. Now, spreading it out by 20 centimeters for the beginning part when it's way over here probably isn't too much of a change, because it's already a meter and then I spread it out. Well, I spread out 20%, so maybe that does change it 20%. But here I spread it out significantly. Here it's really, really close, and it doesn't really show the scaling factor in here. So anyways, maybe I should expect definitely lower potential. That's what I'm after. And maybe quite a bit lower. But as I do this problem, you'll see that these are the same in front. So I'll just do those numbers first. I can imagine factoring these out. And so this would be 9 times 10 to the 9th times negative 7.5 times 10 to the negative 6 divided by 0.2. So that goes in front of, and once I factor it out here, I have a natural log, and I'll just do that in my head, 2.1. I better put a double. Oh, no, it's already there. My bad. Okay. So parentheses, and then it's natural log of 2.1, close, minus, and then I'll have a natural log of, it looks like a 0.20125 divided by 0.00125, close, and I get 1.65 times 10 to the 6 volts. And that does seem to be significantly less than the change in voltage I got when they were point charges. That was 10 to the 7th, 10 to the 6th. So that's a factor of 10. Plus this number is smaller by another factor of 3 to 4. So, yeah, 10 or 40 times smaller or something. Good. But now, hopefully, the logic is pretty straightforward. That then I'll get the change in potential energy by multiplying it by the charge and the change in potential. So the charge that moves within this potential is that negative 5.5 times 10 to the negative 6. And so we're looking at a negative 9.09 joules. And good, I'm glad it's negative, because the change in kinetic energy is the opposite of the change in the potential. So as the potential energy goes down, the kinetic energy goes up. So that's a plus 9.09. And that would be 1/2 mv final squared minus 1/2 mv initial. That's the change in kinetic energy. And again, starting from rest, and remembering that the mass here is still 0.0112. Okay, so that's right here. Let me get rid of the negative. So I have that 9 times the 2, divide by the 0.0112. That would be velocity squared. And so taking the square root of this, we're looking at a final speed of about a 40.3 meters per second. Yes. Nice. All right. So we've done some hard ones. The whole material is hard. And so, again, I'll say the same thing. Hopefully, you've got the first part, kind of the easy part with the point charges. And then the other ones, maybe you've given it a good try with the calculus here. And that's kind of the setup of that. But now we start to get to the applied stuff. And usually the applied stuff is a little simpler. It's just kind of a little more plug and chug. It's a little more, okay, how do you do these type of problems? And so this one, I'm sure you saw coming. I did a lot of examples for you about capacitors and what charges and energy and voltages are on each of them. And so hopefully you learned our strategy of called reducing the circuit. That is, see what you can look at, and we can combine capacitors that are in series or in parallel. And maybe the first thing you noticed right away, I hope, is that the 60 and the 40 are right here in series. And so I would call this circuit right here the equivalent of this one, where I'll just put the 10 microfarad alone, the 100 microfarad alone. But here I have the equivalent of the 60 and the 40. And if you remember, capacitors in series add up this way, that you get the equivalent by adding their reciprocals. On a calculator, I like to think of it this way. Take the reciprocal of the first one, add it to the reciprocal of the second one. And of course, what you're going to get is the reciprocal of the equivalent. So if you take the reciprocal of that, you get the equivalence. And I like this little method because it's so easy to do on our calculator. And so I will go 60 reciprocal plus 40 reciprocal, hit enter, hit reciprocal, and get the answer to say that, okay, this circuit that's got 4 capacitors is the equivalent to this circuit, and maybe I should put 20 volts here, that has 3 capacitors, where the 60 and the 40 have been replaced with a 24. And of course, now if you look at this one, you'll see that the 100 and this 24, which is already an equivalent of these two, are also connected in something nice called parallel. By the way, you might remember I said an easy way to find series ones is if you just took your marker and drew straight and went right to the other without crossing any other line or anything, without having a node, that would be series. Whereas a parallel, you kind of do the same thing to both sides, and so you have to be able to go from one side without lifting up your pen or anything, draw, and without crossing anything else, get to the other one. You could, though, get to nodes so that, maybe something else is parallel. So if you came this way, you'd get here, but going this way, you'd hit the battery first. Oh, so that's not in parallel with this one. But these two are, and so the 24 and the 10 are in parallel. And those are the easy one. The equivalent when they're in parallel is just the sum of the two. And so I won't even need my calculator for that one. I'll just say these two are equivalent to 124. And of course, I haven't touched the 10 yet. And then one more step here. You will notice, again, if I take my marker, I can go from the 10 right to this equivalent 124, and there's no other elements. There's, no battery, no other capacitor, and there's no other node to switch off from. I can just go right there. I can't go anywhere else, so it's called series. And so these two can be put together using this more complicated called the harmonic sum. So I'll take 10 reciprocal, add it to 124 reciprocal, hit enter, hit reciprocal, and get the equivalent of these two. And it looks like I got a 9.25. And I've done all this in microfarads. So these are all in units of microfarads. 20 volts, 20 volts. Now, again, hopefully you kind of caught our strategy here, is that our goal is to really eventually find out what's going on in the real circuit, all four individual capacitors here. Okay. However, each of these are equivalent to that. And so I'll call this the equivalent, I'll call this the equivalent of the equivalent, and I'll call this the equivalent of the equivalent of the equivalent. And so if any of these help me figure out what's on the real circuit, we can fill in this box. And this one here, which is the equivalent of the equivalent of the equivalent, actually is quite useful. Well, what's useful for it, and the reason we like this reduction method, is because if you want to get charge on a capacitor, you could say it's the capacitance times the voltage. And right here we know the voltage and we know the capacitance. So I have the capacitance, at least in microfarads, and if I multiply it by the voltage, I get a charge of 185.1 microcoulombs. Now that, of course, is what would go on to an equivalent capacitance. So how does that help me with the real circuit? Well, realizing that all of these electrons that are going to get on this equivalent one is what must come out of this battery, and coming back to the real circuit, I can see then that whatever comes out of this real battery, which we just said is 185.1, is also what comes into the battery, 185.1. And so it must have come in from this 10 capacitor. So this capacitor here must have the charge of 185. So this would be 185.1 microcoulombs. So that's kind of the first step in solving this problem, by saying, okay, looking at this equivalent of the equivalent of the equivalent circuit, I can get how much charge is actually on capacitor of the 10 microfarad capacitor. Now, sadly, it doesn't tell me how much is on the 40 or the 100 or the 60, because this 185 comes and it kind of splits off, and some of it goes to the 40 and some of it goes to the 100. So really the only thing I know is that the sum of these two is going to be 185, or individually they are less than 185. So I really don't know about the 40 or the 100 yet. And for that matter, then whatever goes on to the 40 gets chased off and goes on to the 60. And so the series here tells me, and I like to put kind of a little marker here to remind me, that the 40 and the 60 are going to have the same charge, which is going to be less than the 185, but I still don't really know what that is. I just know it's less than 185, but I know they're the same. So if I could find one of these, I know the other, and then I would also know this, because these two got to add to 185. But I'm kind of stuck here for a moment. So maybe I'll try a different part of my puzzle. I do know this, that there's a mathematical connection between these three, and so if I know any two, I can find the third. So I'll take advantage of that, because by finding this number and knowing this number, I can get this number. And you see it right here. The voltage then would be the charge divided by the capacitance. So if I take the charge of 185.1 and divide it by the 10, which I suppose I don't need a calculator for that, but I used it. This should be 18.5 volts. Okay. So that's kind of nice. But how does that help me? Well, just like we had a conversation about charges, we can have a conversation about voltage. And we can even look at this circuit here. This is where this circuit would help us, the equivalent of the equivalent. Because what this is saying is this battery is pushing things with a voltage. The voltage comes from the electric field. You might say it has a push of 20. That means these two have an electric field in series pushing back with a total of 20 also, was our argument. We argued it kind of like with a gravitational potential energy, that if this was like a little hiking trail and you and a buddy went here, if one of your friend or your buddy goes up to the top of the mountain and they go up 20 meters, and you take a different path and you go up and then up again, your total is going to be 20. Now, that doesn't tell you what these are individually, but you know you have to get to the same height. You have to get to the same energy level. Of course, that's gravitational potential energy, but we can use that for electrical potential energy and then say that these two have to add up to 20. And we already know this is 18.5. So if this is the majority of the height, 18.5, this must be the 1.5. Now, of course, this is not the same as any one capacitor here, but it's in parallel. So if we take this information back to here, we could say that there is a 1.5 volts across this capacitor, the 100, and also across this one, because they're in parallel. They have the same voltage. And the 100 is where it helps us. So we know that this is 1.5 volts here. And by the way, that same logic tells me that this 24, which is the equivalent of these two, or if we think of it in terms of gravitational potential energy, you and your buddy go for a little hike. If you go this way and go up 1.5, your buddy's got to go up this way and go up the total of 1.5. So these two voltages together add up to 1.5. So these two add to 1.5. They're not the same voltage, but they have to add to 1.5. Okay. So I'll keep that in the back of my mind. By the way, I'll go back to that idea that if I never know two of these, I can find the third. So now that I found the voltage on the 100, why don't I get the charge using this formula here? Okay, so I'll take the capacitance, 100, and multiply it by the voltage, 1.5, and get 150 for the amount of charge that goes on to the 100 microfarad capacitor. Now, if you remember earlier, using conservation of charge, we said 185 comes out of here, and so these two have to add to 185. And if we just say this is 150, we can take the 185 and subtract the 150 and end up with 35.1. And we said that the 60 and the 40 are in series, are going to have the same value. So now we have the charge on the 40 and the 60. And we also then have 2, and we can get this last piece, well, not counting these. I'll get to the energy in a moment. But I can get to this here and say, okay, well, how much voltage is there? And we'll use this. We'll take that charge, which is 35.1, and divide it by its capacitance. And so for the 40, I'll get a 0.878. And for the 60, it would be 35.1 divided by 60, and that would be 0.585. Now, remember earlier we said that these two voltages, kind of as a check here, should add up to this one. And so that'd be a, 13, good. 14, well, I'll just put it on the calculator. I don't have to mess with it in my head. Is that 1.5? Close. And so other than maybe some rounding here, makes me feel good. And so within, very, very close. And so I'm going to call it a rounding and, okay, that is my charge. Actually, if I rounded it up, I think I would get it because I just copied it without rounding. Cool. But I think that'll just round it up one more. Anyways, but other than rounding, I think it's right. Now, if you wanted to, you could probably use the fact of like this one here. This is the equivalent of that one. And if we think of this as one capacitor, knowing its voltage is 1.5, we could get its charge by taking its 24 and multiplying it by 1.5 here. And say that it's 36 went on to here. And so 36 went in this direction. And if we compare this equivalent one to this one, we can say that the 36 went on there. And again, that's about the same. And so 36 would have worked too. It'd round a little bit high in terms of adding up charges, but it would make this voltage come out a little bit more better. So more better. Terrible grammar there, but it would be better. So we got rounding one way or the other. So if you got 35.1 or 36, it just kind of depends on what direction you went here. And all those are fine. In fact, maybe I'll just kind of double check this. Like I said, using energy, these two should add up to 1.5. Okay, they do within rounding. This one and this one, which would be like going up this path, should add up to 20, and they do. Or this path, up here, and up here, should add up to 20. So this, and this should add up to 20. And they're, other than rounding, they're pretty close. So based on conservation of energy, I'm happy with that. And also conservation of charge, 185 comes out, which should be the one on the 10, and so that is good. And then it comes and it splits off to the 40 and the 100, and so those should add up to 185, which they do. And then the 40 sends it right into the 60, so they should have the same, and then so they add up. And so these are one of these problems I was saying. You can pause here and check and know if you got it right or wrong. Now, that doesn't mean you're going to, if you have got it wrong, if you're going to be able to figure out what you got wrong and get the right answer, but it does mean you have a pretty good idea at this point whether you got it right or wrong. And so I like that one. Now, the energy is this, 1/2 CV squared, although we also had the equation 1/2 QV. We also had 1/2 Q squared over C. So we could use any of these three. My favorite one is this one, so I guess I'll use it to get the energy on each capacitor. We can just go straight across, but I thought it might be nice maybe to get the total energy on the equivalent, because that's what these total energies should add up to, and that'll be kind of my check. So looking at this circuit, which is the equivalent of the equivalent of the equivalent, and putting in some numbers here, 1/2 times the capacitance, 9.25, times a voltage of 20 squared, gives me about 1,850 microjoules of energy. Okay. So if I do the same equation for these, 1/2 times C, which is 10, times its voltage, 18.5 squared, that's the bulk of the energy. Kind of makes sense. It's the bulk of the charge and the voltage there. Makes sense too. It fills up. It's such a tiny one. It fills up so quick. It kind of dominates the whole circuit here. 0.5 times its capacitance times its voltage of 0.878 squared gives me about a 15.4 microjoules of energy. 1/2 times C, that's the 60 times its voltage, 0.585 squared, gives me about a 10.3. And then the last one, 1/2 times C times its voltage, 1.5 squared, is about 112.5. And maybe just to check if these are adding up, I'll add that one to the 10, to the 15, and then to the 17, 11, and adds up. Yeah, so 1849.4, which is very, very close to adding up here, which again makes me feel real comfortable with that being the right answer. Okay, well, let me go on here. Like I said, it's a long test. I'm glad you had 2.5 hours to do it. Even me talking through it, it's taken at least, well, we're at 1.5 hours now. So hopefully you didn't try to watch this all in one sitting. But let's go to the last problem. And this is, of course, also out of chapter 26, where we have capacitors here. And it's filled with nylon, and hopefully what you did is kind of the basic definition of a capacitor, and then I'll just call it the air-filled capacitor, or the free space. We just take charge and divide it by its voltage. And then we said if you have some material in it, you can just multiply by its dielectric constant. So that's what I'm going to do, especially since we did this one in lecture. What is the capacitance in free space? Of course, to do that, we need to get the voltage. So we're going to have to go back to chapter 25 and integrate the electric field. And so if we have kind of a coaxial cable device, we have to take the electric field from the radius of the inner conductor to the inner radius of the outer conductor. And if we do that, we'll just have EDR. And depending on which way we go and which way it's charged, this dot product will give me a cosine of 0 or a cosine of 180 degrees. And not paying attention to that, because that's either a +1 or a -1, and even ignoring that negative, we can just say that the definition of capacitance is the charge divided by the voltage, and it's just the magnitude of the charge divided by the magnitude of the voltage. And so I'll just say, let's just go straight out, and whether I'm with the field or not, call it a positive or a negative, and just drop it. Here's a negative, drop it. Now we will have to go back one chapter and remember the electric field that's perpendicular to a charged rod. And it has to be a long one, but I guess this is pretty long. This is, 100 meters long. And so I'm just going to throw that one out there. We could go back to Gauss's law and re-derive it. And you might have to during the test, or you can open up the book here. In fact, maybe I'll just kind of grab the book here. I'll go into chapter 26. I mean, because here it is. Here it is, example number 1. Here is the cylindrical capacitor, where we, have it. And I guess we're right here at this step here, and we're going to just look up the electric field. Oh, now he writes the electric field in terms of Coulomb's constant, but we're kind of doing the same thing. And we're going to get this one actually right here, right? So I suppose you could have memorized the book, but again, don't expect you necessarily to memorize the book here and know where it is. So if you did, great. If not, that's fine too. But you can see by this integration, the lambda 2 pi epsilon naught, and then we have an integral of dr over r, which is a natural log of r, evaluated, and I'll just go from A to B. And so from the radius of the inner conductor to the inner radius of the outer conductor, and taking advantage of the property of logarithms, we would have then the natural log of B minus the natural log of A, which I will write as a quotient. Okay. So there's the voltage between them. And so, again, like you might have struggled with in chapter 26, we've got to use Gauss's law from 24, and we got to use the idea of voltages and potentials in terms of chapter 25. But when we put those together, we can get something practical for our capacitor. So the capacitance then would be the voltage, which I'll write as lambda over 2 pi epsilon naught ln B over A. And then over the charge inside. And so if we have this coaxial cable that has some, length L and some charge per unit length of lambda, the charge inside is lambda over L. And so the lambdas go away. Kind of simplifying our compound fraction, we have the same equation that, like I said, you could have just looked up into the book, but wasn't really expecting you to do that. And so this is the capacitance for this long cable. Now, this is, of course, without any material. And so we still have another step to take. But let's see what number we get right now. And so grabbing my calculator here, I'll take the 2 times the pi times the permeability of free space times, and I need to check this, length of the cable. Yeah, I've got a 100-meter long cable. And divide it by the natural log. And let's see. The outer radius. Okay, here we go. The outer conductor's inner radius is 2.75, and that's in millimeters. So since we're taking a quotient, we just have to make sure those are in the same units. We don't have to be in meters. So I'm going to go ahead and use the millimeters, because then I divide it by 1 millimeter. And it looks like I come up with about a 5 point and around to 50. So 5.50. And it's 10 to the minus 9, which I will write as nanofarads. And now, of course, to finish part A, we just have to multiply it by the dielectric constants. And so the nylon would reduce the field by this factor of 3.4, which makes the capacitance a little bit higher. Now my calculator writes it as 10 to the minus 9, but I'm going to just move the decimal in my head. So that'd be 18.7 nanofarads. And so there is A. What is the capacitance of this long cable? And then for B, again, like we worked out in class or the video lecture or also in the book here, is we have a maximum strength. The maximum strength is the maximum the the field can ever be. And it says it cannot exceed, what's the maximum? 14 million volts per meter. So that means the electric field has to be less than 14 million volts per meter, wherever the nylon is. Now, keep in mind the equation for the electric field, which we put right here, was 1 over 2 pi epsilon naught lambda over r, and that has to be at all locations less than 14 million volts per meter. Now, what I mean by all locations then is within here we have different radii, and according to this equation, the bigger the radius, the smaller the field. So we're in danger of exceeding this big number right at the surface of the inner conductor. In other words, where R is the smallest. So we want to focus our attention right here at this 1 millimeter mark, because we have to be less than 14 million at the 1 millimeter mark, and for that matter, everywhere within this coaxial cable. But if we're less than it at the 1 millimeter mark, that means we're also less than it at any other location in here. And so I'm going to then put 0.001, and I am going to convert it to meters because I'm going to use epsilon naught in meters and in newtons. And that has to be 14 times 10 to the minus 6. I've kind of run out of space, so one more piece of paper here. Call it 5B. This tells me that lambda for my coaxial cable must be less than, so grabbing my calculator here, I'm going to go 14 times 10 to the 6th times 2 times pi times 8.85 times 10 to the negative 12, and then times 0.001. So again, let me point out, I'm converting that to meters because I used the epsilon naught in terms of meters here. All right. And so this needs to be about a 7.78 times 10 to the minus 7. Okay. Now, there probably should make a little subtlety here that's a little confusing, and if anybody does this on the exam, I'll give them full credit. But you'll notice that I just calculated and thought of the electric field as if it was in free space, when it is technically not in free space. There is a nylon piece in here. But the rating is actually done by simply taking two parallel plates, putting the nylon in between, cranking up the voltage until the material disintegrates. And then they just take that voltage between the two plates and divide it by the distance, and that's how they get the electric field. In other words, the electric field rating is based upon what the electric field would be if it was free space. So you got to calculate it as if it is free space, even though it is not free space. And that's a little subtlety in these numbers that we didn't really get a chance to go into. So it wouldn't surprise me if somebody puts in a dielectric constant factor here. And if you do that, that's perfectly understandable. Technically not correct, but nothing that I would take points off for, because it's not your fault. It's something that's a little subtlety that we just haven't had time to go into yet, and probably won't at this semester, but we will talk a lot more about next semester, or you won't have me next semester, but when you transfer next semester, then you'll talk about, okay, how do we really mean these measurements, and you'll end up with electric field and also displacement field, and there's some fun discussions with that. Okay, so that's why I used free space here, by the way. So in part B, I'm calculating the electric field based on free space. Now, I'm still not quite done, but very, very close to being done, because now, coming back to what we did earlier, the voltage here, which is this lambda over 2 pi epsilon naught ln of B over A. And now we have found the upper limits of lambda. Let's put in that upper limit and our two radii, 2.27 and 1.00, and this should give us the max voltage here. So 7.78 times 10 to the minus 7, divide by 2, also divide by pi, also divide by 8.85 times 10 to the minus 12. I guess, by the way, this would be half a Coulomb's constant. That might have been easier to type in. But then times the natural log of 2.75, I get about 14,000 volts. Let me just call it 14,200 volts. So on this coaxial cable, I probably would see something that says this, 14 kV. That means it's its maximum rating. Don't go higher than that. Otherwise, you will disintegrate the nylon, which is what you saw me do in class, and that's why I did it in class. That's why I exploded the capacitor, so you can see it explode. All right, well, there was a lot of talking and a long test. Hope you did well. Hopefully you get a lot of partial credit. I have a feeling that's the case. Most people after this exam just feel like they didn't do very well because they didn't get 100% on every problem, but don't let that get you down. It's very rare somebody gets, even one of them completely right, but they get something like 18 out of 20 on all, 5 of them or something. So, they still get an A. They really know what's going on, but they just didn't really quite put every piece together because it's a tough material, a lot of material, and I will eventually get this graded and get it back to you, but I am going to need a full weekend to really grade it, and so that's why this video was made, and it is a long video, and so hopefully you watch it over a period of a couple days. Take care, and see you later. Bye.